then I'll post edit it. So I'll kind of like, if anybody's picture comes up here other than mine, we'll blur that out. So the goal of this activity was to very quickly take us through drawing structures, but more specifically, the skill that I want us to develop is how to quickly assess whether a compound is polar or non-polar. This is very important because as we will see now and we study the properties of liquids, solids, and then later on solutions, identifying a compound as polar versus non-polar is super important for a lot of these concepts that we're going to be studying. For example, the boiling points of liquids, the melting points of solids, the solubility properties of different compounds in different kinds of solvents. So there's a lot of things like that. So let's start out here with these. I have 6 formulas here. And what we're going to do first of all is draw the Lewis structure. And then we're going to determine for each one, is it polar or is it not polar? Now, what I'm going to do is I'm going to go first and look at a couple of them from the point of view of geometry. And then I'm going to use a shortcut that allows you from just the Lewis structure to do a very quick, guess as to whether the compound is polar or not. And it works about 90 to 95% of the time. I'm going to show you an example where it doesn't work. All right, so here we have COF2. So remember that you have to consider these are all non-metals, so this is a molecular compound, right? Secondly, you have 3 different elements. This is not a binary compound. And typically, not always, but typically, the more the less electronegative element is typically the one that goes in the middle. That's not always true. But also what is true is that most of the time, when you look at these structures, typically the first element in the compound's formula tends to be the central atom, with the exception of hydrogen. Because remember, hydrogen can never be a central atom. So remember how we do it. I'm going to do it very quickly here because by now you guys should have a lot of practice doing this. So we have carbon brings in, remember that the way this works is we have to go to our periodic table, right? And I'm going to go to the periodic table very quickly here, just for a quick review how this works. Why are you not? Oh, there we go. It's my periodic table. And again, the idea is that the group number tells me how many valence electrons these guys are going to have. So for carbon, that's 4. For oxygen, that's 6. And then for fluorine, which I can't see right here. Oh, here we go. For fluorine, it's 7, correct? Oops, why is it not working? Whoa. Wow, I'm having a moment here with this thing. There we go. Wow. Okay, it's not working out. I'm sorry. My stylus is not picking up things. In any case, let's go ahead and come back here to our little whiteboard that we set up. So basically, we have 4 from carbon plus 6 from oxygen plus 2 times 7, right, which is 14. So that gives us 26 electrons. We're going to put carbon in the center. We're going to connect fluorine. We're going to connect fluorine. We're going to connect oxygen. That gives us 6 electrons, right? Remember that we count each one of these as 2. We have 2, 2, 2 is 6. And now we're going to place the rest of the electrons as dots. So we need to put essentially 18 of them. And we start around 1, 2. Okay, I'm going to turn this around a little bit so I can get a better grip. Maybe go a little slower. I can get this. 1 second. Let me see if I can get this to behave you a little better. Make it a little thicker. Okay, so here we go. 1, 2, 3, 4, 5, 6. 6 over there. 6 over here. And that gives us, let me fix this a little bit here. It looks kind of messed. There we go. Let's fix the oxygens here. 2, 2, and 2. Okay, so that completes our 24 electrons. That's 8, 8, and 8. That's 24. But the carbon is missing something. Now the question is, where do we borrow electrons from? Remember, fluorine is a very electronegative element. It doesn't want to give up electrons. It wants to take them. So that means that oxygen is going to have to be our guy. So what we're going to do is we're going to borrow a pair of electrons from there. So I'm going to erase that. And I am going to put them in here as part of a double bond with the carbon. There we go. So that's our structure. Now, the next question is this molecule polar or not? Remember, there have to be two conditions. One is, right in here. So a polar molecule has at least one polar bond. And that means a bond that is established between two elements that have, considerably different electronegativities. And there has to be a non-symmetric. So the polar has more than one and is not. Let me see if I can make this thing right here. In other words, the distribution of polar bonds is not symmetric. I showed you in class carbon dioxide, CO2, which has two polar bonds between the oxygens and the carbon, but because it's a symmetric compound, in other words, those bonds are kind of like symmetrically opposed to each other, the electronegativities cancel out, right? So we have this guy here, and we're looking for this idea. So first of all, are any of these bonds polar? How do we know? Again, just if you guys have a hard time with it, just go back to the periodic table. All right, and you compare electronegativities here. Okay, let me get this out of the way here. All right, compare electronegativities. Here is oxygen at 3.5. Here is fluorine at 4. And they're both going against carbon, which is 2.5 electronegativity. So that means that both the oxygen carbon and the fluorine carbon bonds have an electronegativity difference that is greater than 0.4, which is kind of like our arbitrary threshold. And that means that all those bonds are polar. So let's come back to our table here, our little board, and we're going to say that these bonds, and let's see if I can find a different color here. Let's use this one here. That bond is polar, pointing towards the fluorine. This bond is polar, pointing towards the fluorine. This bond is polar, pointing towards the oxygen. Remember, we arbitrarily, or I guess more out of concern for physics, we're saying that the electronegativity dipole points towards the negative end. Now, that in and of itself does not make the molecule polar. The question is that group of polar bonds distributed non-symmetrically? So let me do this. Let me come back here. and I'm going to redraw that structure again. Okay, we said we had C, we had O here, we have F, and we have F. I'm going to put the lone pairs in there. Although for the purpose of the geometry of the molecule, it's not as important unless the lone pairs are on the central atom, which we don't have any right now. Now remember, our goal now is we go to this other chart that I gave you. And by the way, just so you know, I'm a nice guy. So in the case of a, where is my VSEPR chart? Oh my gosh, I forgot to put it up. Okay, hold on a second. Let me go call that up. Hold on a second. I got it. I forgot to. I thought I had pulled it up. Oh, yeah, I do have it. Hold on a second. I know why it wasn't working. There we go. Okay, I'm gonna get it now. Share. We're gonna do our. I gave you this table for you to use, and in an exam, by the way, I'm gonna give you the same table. You don't have to memorize it. I just want you to know how to use it. We may put a little more information later on, but for the moment, remember the way the VSEPR chart works. Remember, VSEPR means valence shell electron pair repulsion. It's a theory by which we approximate the shapes of molecules by proposing that the clouds of electrons that are bonded around the central atom, they repel each other, and because of that, they find positions that minimize the repulsion and thus generate the different shapes that we see. So in this case, we are looking for a compound that has 3 electron groups around it. It has carbon in the middle, and then you have an oxygen, you have fluorine, and another fluorine. Remember, it's not the number of bonds. The O is double bonded, the fluorines are single bonded. It doesn't matter. What you're looking for is groups. So in this case, we have essentially 3 groups around. And so we find this type of structure here, the trigonal planar type of structure, because there's 3 groups around it. And there's no lone pairs, so that means that this molecule is going to have a trigonal planar shape at an angle of 120 degrees. Now let's go back. Oh, I'm sorry. I'll go back that way. Let me go back to our little board here. Okay, so now we have the right way of drawing this would probably be more along the lines of this. We would have, let's say, the C there, we have an F here, and we have an F here. And now I'm going to put, just for the satisfaction of the crowds here, let's make sure we put those electrons in there just so that you don't get lost here or think that I'm trying to trick you. Okay, now that is the correct shape. Here is what we see. The molecule has polar bonds. We said that all of these bonds are polar. Now there's a little bit of a difference here because we said that these bonds with fluorine are actually more polar than the bond with oxygen. You have polar bonds. Is the molecule symmetric or not? Well, it isn't, because although the shape is perfectly trigonal planar, what occupies this position over here is an oxygen, whereas what you have down here are fluorine and fluorine. So in other words, they're not the same. They are not the same. And therefore, we would say that this molecule is essentially not symmetric. Symmetric means essentially that you have the same things on both sides of some kind of an axis, right? And the reality is that they're not. There is, if you think about, if you were to draw an imaginary line through here, you can see that what's on the bottom side of that line and what's at the top of that line is not the same. So therefore, this molecule is not symmetric. And so we can go back and say with confidence that this molecule here is going to be polar. All right, that's the way it works. Now let me know if there's any questions. I'm going to go quicker on the other ones because I'm going to use a shortcut.
Dr. D, I had a quick question.
Yes.
Does the double bond of the oxygen matter in the symmetric part of this?
That's a great question, and the answer is for most of the work that we do, no, it doesn't matter. It doesn't matter whether the atom is connected via a single, double, or triple bond. All we care about is what is essentially that cloud of electrons doing. Um, in more advanced courses, you would consider the sizes of the atoms and that kind of thing, but for us, this will be sufficient. Okay, good question.
Okay.
Yeah, so when you subtract, for example, the electronegativity of oxygen minus the carbon, right? What is it, 3.5 minus 2.5, it's only one time. You don't do it twice you don't do it for each bond. Okay? If you want to do that method. Okay, now I think that I gave you guys at some point something that looks like this. It may not be the same image, but it's kind of like I went through this in the video that accompanied your little exercise that you did on molecular shapes. And this is a shortcut. Like I said, it's going to work most of the time. There are a few exceptions. You have to be careful, particularly when you go into the bigger molecules that have multiple bonds, more than 4 bonds. For molecules with an octet, it's pretty straightforward. But when you have to expand octets, it gets a little tricky. So here's the way it goes. The first thing you do is you ask yourself, are there any polar bonds in the molecule? If there aren't any polar bonds, then there's not going to be any polarity. So by default, you go to the left side here, and you can see that is going to be nonpolar. So you don't have to do anything else. If the bonds are nonpolar, then the molecule is nonpolar. Now, let's say that there are any polar bonds, at least one. Then you ask a second question. Are they distributed symmetrically or non-symmetrically? Now, without doing the actual shape of the molecule, many times you can take a shortcut. You can ask, are there lone pairs on the central atom? If the answer is yes, then we're going to say that the lone pairs on the central atom most of the time are going to make the molecule non-symmetric. So we go on the right side there. And that means that because you have a polar bond and the molecule is not symmetric, the molecule is polar. Notice that I bypassed looking for the shape of the molecule. I simply looked at the question, are there any lone pairs on the central atom? Now, let's say that there aren't any lone pairs. Now what I'm going to ask is another question. You can see it here kind of like in the middle of the almost bottom line. Are there different bonded groups? In other words, are the groups that are bonded to that central atom different? So it's different things connected to it. So the answer is no. In other words, if everything around that central atom is the same, then the molecule is symmetric, and even though there are polar bonds, the molecule is nonpolar. If there are different things bonded to that central atom, the answer is yes. You go to the right side, that molecule is not symmetric, and so it's going to be polar. So this is kind of like a quick way of doing things. And if we look again at that little exercise I did before, let's go back there. Where are we? Here we go. If you look at this guy here on the left, right? And again, it's just kind of like complicated. First of all, we decided, let me erase a few things here just to make it a little less congested here. Okay. So we established, number one, that there are polar bonds in here. Now we ask the question, are there any lone pairs on the central atom? The answer is no. Then we ask, are the atoms connected to the central atom the same or are they different? The answer is they're different. And as a result, we arrive at the same conclusion, the molecule is polar. See, I didn't have to go to the VSEPR table and find out the shape and see how things were distributed. right? I didn't have to measure out geometrically how the dipoles are lined up and that kind of stuff. I simply took a shortcut. So let's try that with the next one. Let's try Ni3. I'm going to try to do a structure for this. Now, I'm going to skip the whole sequence of how to get to the structure because you guys should know how to do it. So we're going to have nitrogen. We're going to have I. We're going to have I. We're going to have I. And we're going to have a dope. I'm sorry. Let me go ahead and put the different lone pairs on these guys. Again, I kind of took a shortcut here. You can confirm later on that this is going to work, right? Okay, so we got this guy here. So again, I'm going to look at it. Are any of these bonds polar? Well, let's go to the periodic table. And let's find out. Here's our periodic table. Okay, here is nitrogen at 3.0. And here's iodine at 2.5. So that's a 0.5 difference that qualifies as polar. Remember, we used 0.4 as the threshold, but it's kind of like a little, that's very arbitrary. You know, you can probably in some environments say that a 0.4 difference is polar. We pretty much, this is all approximation anyway. Remember that these electronegativity values that we have in here, this is just a scale that Pauling made, and it's very kind of like the same as saying, okay, on a scale of 1 to 10, blah, 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 whatever. You know, it's a little subjective. But anyway, let's go ahead and go back here and say that essentially in this molecule, all of these bonds are polar. So we have polar bonds. Criterion number 2, are there lone pairs on the central atom? The answer is yes, there are, right? We have lone pair in there. Now, if you look at the VSEPR table and the molecular shapes, yes, you're going to get that this is a trigonal pyramid, right? And so you're going to be able to see that those polar bonds are pointing all upwards. But based on our criterion here, since we have a lone pair and we have polar bonds, we're going to predict, we're going to predict that this molecule is polar. You can go back later on and check it against the what do you call it, the VSEPR table if you want, if you feel so inclined. Let me move this guy a little bit out this way. Here's the next one, HCN. All right, so we're gonna do that one first. Let's see, we're gonna draw here. Okay. So again, I'm gonna take a shortcut to the actual structure. And we're going to find out that this is the structure of, oops, this is the structure of HCN. Once more, let's go to the periodic table and find out. We find that the electronegativity difference, electronegativity difference between H and C is 0.4, but for all practical purposes, we've decided that we're not going to consider that to be a polar bond. On the other hand, the carbon-nitrogen bond, that's an electronegativity difference that is significant. And so we are going to say that this particular connection here is polar. Let me do something. Let me put it upwards here so you can see it a little better. So we're going to say that this is a polar bond. Now remember, we're not concerned about the nitrogen on the outside. We're concerned about the central atom. So we're going to ask, are there any lone pairs on the central atom? The answer is no. So then we ask, well, is everything that's connected to that central atom the same? And again, I don't mean numbers of bonds, I mean the types of electron groups. Well, we have a hydrogen on the left. We have a nitrogen on the right. They're not the same. There is a polar bond. And so we're going to say that because of that criterion, this molecule is polar. See? Now, I can go back to the VSEPR table. I can determine that this structure is linear. And because it's linear, when you add, quote unquote, the vectors of polarity, you're going to get a net polarity pointing towards the right side, towards the nitrogen atom. And that will confirm it. But if all I want to do is establish whether something is polar or not, without having to quantify it, this is sufficient. Okay? Questions? I'm not going to do them all. I'm going to do 2 more and that'll be it. Okay, let's do this one here. IF5. That's a cool one. You already can tell by looking at it, you have iodine, which is a big atom, and you have 5 atoms connected to it. And it's fluorine, who doesn't give up double bonds. You can tell, you know what, this is probably going to be one of those expanded octet molecules. Again, you have each one of these has a valence of 7. So we have 5 and 6 times 7 is 42. So we're going to put, let me see if I have this correct. I'm going to put the iodine in the middle. Actually, I'm going to have to give myself a little more space here. Let me erase this stuff that I have here in the bottom. This is the one where we were using VSEPR to establish the shape of this guy. Oh, yeah. There you go. There you go. Okay. Okay. So IF5 is what we're going to do. So here we go again. So we have I, and then we have 5 fluorines around it. We're going to put lone pairs around all of those fluorines until we complete octets. Oops. Sorry, some of my dots come out a little like lines. And the last one. Oops. Let me do something. Move this guy a little bit to the side here. Okay. Back to our drawing board. Okay, so each one of those fluorines and the bond with its 3 lone pairs and the bond to the iodine gives me 8 times 5 is 40, but I had to commit 42 electrons to this. So that means that, let me make sure that looks like an I. That means that I have to put an extra lone pair in there on the iodine. Now this is one of those weird ones. But again, if all I want to know right now is this molecule polar or non-polar? I'm going to ask again. Are there any polar bonds in this molecule? Are there any polar bonds in this molecule? And the answer is, well, actually, yes. All of these bonds are going to be polar, and they're pointing towards the fluorines. Right? And now I'm going to ask, does the central atom have a lone pair on it? And the answer is, yes, it does. There's a lone pair in there. So that would mean that my molecule is not symmetric, and therefore it's going to be polar. Now I'm going to come back and confirm that in a few moments because first I want to do the next one, XEF4. Okay, so that's my prediction. My prediction is that iodine pentafluoride, IF5, is a polar molecule. Now, let's look at the next one. Scroll over here. Let me see if I can move this guy here. Over here. Now, this is interesting because here we have none other than a noble gas involved in a covalent compound, which is kind of very unusual, correct? So let me move this guy out of the way again because I put it too far out. There we go. So we have a xenon, and we have fluorines. So we're going to go F, F. And again, when I draw Lewis structures, I don't start out by drawing the shapes. I don't use those special wedges and things to signify, three-dimensional type of thing. Now, xenon technically would be a noble gas, so it has 8 valence electrons. And of course, fluorine would be 7 times 4 is 28. So that means that I have 36 total electrons that I need to place in here. So let's start out. Let's put the fluorine. Okay, that's 6, and that's an octet. 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 So that would be 4 octets. That's 32 electrons. So 36 minus 32 is 4. So that means that I have to put 2 lone pairs on that xenon central atom in there. And now I ask, is this compound polar? Well, it has, first of all, polar bonds, right? Because fluorine is the most electronegative element there is. So any bond involving fluorine is going to be polar. So let's go ahead and do that. And let's say that you have, those are polar bonds. And now you come to the next question and you say, are there lone pairs on the central atom? And the answer is, yes, there are. There's actually 2 lone pairs. Okay. So, by all of our shortcut ideas, this would be not symmetric. And therefore, so it should be polar. I told you guys that shortcut only works about 90 to 95% of the time. So let's do this. Let's take a look again at our IF5 molecule, which as you can see has 1, 2, 3, 4, 5, and plus the lone pair is 6 electron groups around it. And, let's look at the XEF4, I guess xenon tetrafluoride, which also has the 4 fluorines and the 2 lone pairs, so that's 6 groups around. So let's go back and look and see how does that get arranged when you look at the VSEPR table. And this is where we're going to be disappointed. So remember, we're looking for 6 electron groups overall. So according to the table, we look on the left side here, we look for 6. That's the steric number, right? The number of electron groups around the central atom is 6. But in our case, we had one that had a lone pair, and that was the IF5. And I don't know if I can draw on this. I don't know how to draw on this. So this would be a square pyramid, right? So IF5 is built on a basic octahedral type of shape, but what it does is, because of the lone pair that it has, this, because of that lone pair that it has in here, it ends up being a square pyramid. So notice that that is truly non-symmetric. In other words, I have four groups around this square in the middle. I have an atom on one side and a lone pair on the other side. So that is definitely a non-symmetric molecule. So we are safe to go back and confirm that when we did our prediction, which was based on our little shortcut, we would say that, you know what, this is correct. Yes, it is polar. Now let's see what happens with the next one, with XEF4. Now this one has, again, 4 fluorines and 2 lone pairs, so that's 6 electron groups around it. So let's go to the VSEPR table again and see what that does. So that's 6 electrons, but now we have 2 lone pairs. And here's what happens. Watch what happens. This molecule should now be square planar because it has 1 lone pair here and 1 lone pair there. But no, oops, sorry. That didn't quite work. Hold on a second. I missed the layup. But notice what happens. You have essentially those 2 lone pairs are on opposite sides of that square, and that square has the same atom at each corner. These are all fluorines, and then you have the lone pairs. So it turns out that for this particular molecule, those 2 lone pairs are symmetric with each other. They're on the opposite sides of the same square, which is made at its corners by the same kinds of atoms. Therefore, we have to go back and say, coming back here, that this was incorrect. So let's come back here and say, tell you what, dude, you are incorrect. It turns out that this molecule, again, based, oh, I'm sorry, I'm going to use text here. So what we see is that based on our VSEPR, sorry, I can't barely type, based on APR, no, it is, I'm sorry, let's say no, it is symmetric, therefore not polar. All right. So, like I said, this is one of those situations where the shortcut that I gave you doesn't work. So what I would do is I would say is, apply the shortcut, but whenever you're dealing with any molecules where the steric number, in other words, the number of electron groups around the central atom is 5 or 6, go back and check it. Be very careful that you double check after you've done your shortcut approximation because of the way that these lone pairs get arranged in these larger molecular shapes. You might end up with the lone pairs themselves being set up in a symmetric situation. Let me give you another example of how that can happen. Go back to the VSEPR table, and here we go. Here is another one, the linear shape. So if you have 5 electron groups around the central atom, and 3 of those are lone pairs, what you're going to end up seeing is that because they get placed exclusively at the corners of this equatorial triangle, you end up with a molecule that has those 3 lone pairs arranged in a perfect symmetrical triangle, and then the other 2 groups being up here. Now, I'm assuming in this case that X and X are the same element. If they're different elements, no, you got non-symmetry. Okay, so again, be careful when you do these kinds of structures with molecules that have a steric number of 5 or 6. Be very careful when you do the approximation that you don't land in a situation like these where the lone pairs themselves are set symmetrically, and therefore your shortcut will not work. Okay? All right, I'm going to come back here and see if there's any questions. And I'm
I
going to
had
stop.
a curiosity question.
Sure.
So regarding the lone pair, it makes the compound not symmetric because of the repulsion.
Well, the repulsion is one thing. It makes it non-symmetric because it causes the polar bonds to be distributed non-symmetrically, right? So symmetry, non-symmetry has to do not with the strength of the electronegativity, but with the way it's distributed. It's more of a geometrical kind of thing than a, force or energy kind of thing. All right?
Okay, got it.
Okay. Tell you what, I'm gonna stop the recording here.